Have you ever experienced an application that starts fast but gradually slows down over time, eventually crashing or becoming unresponsive? This frustrating behavior often points to a common but insidious problem: memory leaks. Memory profiling techniques identify leaks by meticulously monitoring how an application allocates and deallocates memory throughout its runtime. Specifically, they look for memory blocks that are allocated but never properly released, even after the program no longer needs them. This accumulating, unreleased memory is the hallmark of a leak, leading to performance degradation and eventual system instability. The core mechanism behind this detection lies in tracking memory allocations and deallocations. A memory leak occurs when a program fails to return blocks of memory to the operating system or the memory manager after these blocks are no longer in active use. Profilers achieve this by taking periodic snapshots of the application's memory usage and heap structure. By comparing these sequential snapshots, they can identify objects and data structures that have grown continuously without corresponding deallocations, indicating that references to this memory have been lost, or that the memory is no longer accessible by the running program, yet it remains allocated and unfreed. This phenomenon creates what is often called orphaned memory, which cannot be reclaimed by the system's garbage collector or memory manager. To practically use these insights, you would typically begin by running your application under a memory profiler. The profiler would then collect data on memory usage, object allocations, and reference graphs over a period of time. Afterward, you would analyze the collected data, often looking for patterns like an increasing number of allocated objects of a specific type or a continuously growing heap size that does not decrease after certain operations. Most profilers offer visualizations like flame graphs or heap dumps that highlight objects holding onto large amounts of memory or displaying unusual growth patterns, making these persistent allocations easier to spot. A key concept in this process is the object graph, which represents how different objects in memory refer to each other. Profilers can traverse this graph to identify root causes of leaks, often highlighting specific objects that are unintentionally being kept alive by a strong reference when they should have been garbage collected. Understanding these reference chains is crucial because it goes beyond just seeing that memory is growing. It explains why it is growing. Another advanced technique is called statistical sampling, where the profiler periodically samples the call stack to determine where memory allocations are occurring most frequently, helping pinpoint the exact code paths responsible for memory retention. Ultimately, memory profiling techniques empower developers to transform mysterious performance slowdowns into actionable insights. By systematically identifying and understanding the precise source of unreleased memory, you can optimize your applications, ensure their long-term stability, and deliver a consistently smooth user experience. This diagnostic approach not only fixes current issues, but also strengthens your understanding of memory management, preventing future leaks before they even appear.
If this helps you fix faster, like, subscribe, and keep debugging with us.